Yes, my dear students, you're welcome once again. In this lesson today, we're going to be looking at deriving equations using the knowledge of dimensional analysis. So, when you're using the knowledge of dimensional analysis to derive equations, there are some things that you pay attention to. In other words, always look out for quantities that depend on others. In other words, if one has an idea about the factors upon which a given quantity depends, the method of dimensional analysis can be used to derive equations. So, the most important word here, the most important thing here is the word depends. In other words, those factors on which a given quantity depends. Now, let's look at this example. Example number 1. It says that consider the oscillation of a simple pendulum of the period capital T may depend on the mass m, length L, and the acceleration gravity g. Derive an equation for the relationship between. Now, from this statement here, we find out that T depends on. So what you simply say that if T depends on M, L, and the acceleration gravity g, then it means that we simply come up with the proportionality symbol, and we simply write this one as T is proportional to M, L times the g. However, we simply we raise these factors to given powers. So we shall simply say that this is m power x, l power y, and then g power z. And then afterwards, you simply remove this proportionality symbol by putting that an equation that t is equal to a constant k, m power x, l power y, and then g power z. And this is our equation. That is the equation that we are looking out for. So what we need to find out is the value of x, y, and then the z. The knowledge of dimensional analysis may not enable us to find the value of the constant k, so we shall simply leave that one in our equation. So we're going to find the dimensions of period capital T, m, l, and g. So this is what we do have. So if this is our equation 1, we shall simply say that the dimension of capital T must be equal to the dimension of the constant k times the dimension of m power x times the dimension of l power y times the dimension of g power z. Now remember that period capital T is time, meaning that its dimension is capital T. This is a dimensionless constant, so shall simply have it as 1 times the dimension of the mass m is the capital M power x times the dimension of L, which is the length, is capital L power y, times the direction of the dimensions of the acceleration gravity g. This is the acceleration, so its dimension is capital L t power negative 2, everything to the power of z. So rearranging this, it's the same as capital T is equal to m power x, l power y, times l power z, times capital T power negative 2 z. And this is the same as capital T is equal to m power x times l power y plus z. I'm simply simplifying this one for all of us to follow. Then times t power negative 2z. Remember that when multiplying values which are having the same base but with different powers, simply add them. Now when you reach this step here, we're going to simply equate powers. So we shall simply say that equating powers to find the values of x, y, and z, we shall begin for t. For capital T, the power of t here is a 1, so we shall simply have 1 on the left hand side being equal to negative 2z. This implies therefore that our z is simply equal to negative a half. Then for capital M, remember that this one can be written as t power 1, m power 0, t, l power 0. This is the same as m power x times l power y plus z times t power negative 2. In other words, any number to power 0 is equal to 1. That's why I'm putting here the 0, power 0. So continue with our work. For m, on the left hand side, you have the power of m as 0 being equal to x on the other side. So implying that our x is equal to 0. Then for l, on the left hand side, the power is 0. This is equal to y plus z on the left hand side. And this implies that our y is the same as negative of z, which is the same as a negative of a half, which is the same as a half. Therefore, x is equal to 0, y is equal to a half, and then z is equal to negative a half. And substituting all of this in our equation t, in equation 1, we shall simply end up therefore that our t, this implies that our t is equal to capital K m power 0 times L power a half times G power negative a half. Anything power 0 is equal to 1. So our t will be equal to the same as the square root of L divided by the square root of the G. And this is the same as t is equal to the square root, there's a K here, L out of the G as our equation. So that is how we use the knowledge of dimensions to come up with an equation. Okay, let's try this question number 2 together as well. So the question says that experiments to show that the frequency f of a tuning fork depends on the length L of the prong, the density rho, and the Young's modulus y. Using dimension analysis, show that the frequency f is given by that equation, where k is a dimensionless constant. So assume that you've not seen this equation here and just do your normal work. So let's begin. So f depends on L, density rho, and the Young's modulus y. So we shall simply say that our f is proportional to L times rho times the y. But you raise this on to the powers of x, y, and z. You can use any other letters. So removing this proportional symbol, shall simply have that our f is equal to a constant k times L power x times the density rho power y times the Young's modulus power z, and this is our equation. So we need to find the values of x, y, and z. Now, using our knowledge of dimension analysis, we shall simply say that the dimension of the frequency is equal to the dimension of the constant, dimensional constant k, times dimension of L power x times the dimension of rho power y times the dimension of y power z. Now, I'm giving you a quick exercise here. What is the dimension of f equal to? Dimension of k equal to? Dimension of L equal to? Dimension of rho equal to? And the dimension of Young's modulus y. You can pause the video and try out these. Okay, so remember that frequency is got from the formula f is equal to 1 out of capital T, where capital T is the periodic time. So dimension of frequency is equal to dimension of 1 over dimension of T, which is the same as 1 over capital T, which is the same as T power negative 1. So dimension of the frequency is equal to capital T power negative 1. Then K is a constant, its dimension is a 1. It's dimensionless. In other words, L is the length, so its dimension is capital L. Rho is the density. Density is equal to mass out of volume. So dimension of density is equal to dimension of mass over dimension of volume, which is the same as capital M over L cubed. So this is the same as M L power negative 3. So I have my M L power negative 3 here. Then Young's modulus. What is Young's modulus from your O-level physics? Young's modulus is equal to stress over strain. So dimension of Young's modulus will be equal to dimension of stress over dimension of strain. So dimension of what is stress? Stress is equal to force over the area. Remember that force is equal to F. Force is equal to stress is equal to. So remember that stress is equal to force acting point area. So dimension of stress is equal to dimension of force over dimension of area. And our force, remember that our F is equal to MA. So our dimension of force here will be equal to the capital M L T power negative 2 divided by your L squared, which will give us M L power negative 1 T power negative 2. So that is the dimension of stress. And strain, remember that it is the same as extension over the original length, meaning that the dimension of strain will equal to the dimension of the extension over the dimension of the length, which is the same as L over L, which is equal to a 1. In other words, strain is also dimensionless. In other words, all quantities which are got by dividing the same units, by dividing the same quantities, they are dimensionless. For example, the strain, we have just shown this one here. For example, trigonometrical ratios, the sine, the cos, the tan. For example, the refractive index of a material, all those ones are dimensionless because you get them by dividing the same quantities or the same units, which gives you no unit. In short, quantities with no unit are dimensionless. Now, coming back to our work here, we shall simply say that our dimension of Young's modulus is the same as m l power negative 1 t power negative 2, and that is what we get. So continuing with our equation, substituting for the dimension itself, we shall simply have capital T power negative 1 equals to 1 times L power x times m L power negative 3, everything to the power of y, then times m L power negative 1 T power negative 2, everything to the power of z. And simplifying this, we shall simply be having that T power negative 1 is equal to, this is 1, L power x times m power y times L power negative 3y times m power z times L power negative z times T power negative 2z. And this is the same as T power negative 1 being equal to L. Now bring the like terms near each other. Since I'm multiplying, I'll be simply adding the powers. So I have x minus 3y minus z. Then times m, which is y times, plus z. And then t, it is only 1, so minus 2z. From here, we are going to equate powers. And by equating powers, since I have t on the left-hand side alone, I can introduce in the l power 0 times the m power 0. So, equating powers, I'll have that for t, I have minus 1 equals to minus 2z, implying that my z will be equal to a half. That one was big one already. Then for L, I have that 0 is equal to x minus 3y minus z. And then for M, I'll simply have it that 0 is equal to y plus z, implying that my y is the same as my minus z, which is the same as minus a half. So I've got the z, I've got the y. I can now substitute into this equation where I have the x to find the value of x. So I'll simply say that from my 0 equals to x minus 3y, the y is a half, then minus the z, z is also a half positive. Actually, the y is minus a half, so I'll put my half there. So this is the same as 0 is equal to x minus 3. This is plus 3 out of 2, then minus a half. And this will give me my x being equal to a 1, minus 1. Check that one out. So therefore, x is equal to minus 1, y is equal to minus a half, and then z is equal to positive a half. So substituting this into my equation 1, I'll be ending up with my f is equal to constant k times l power minus 1, this is l, then times the density power y is negative a half, then times the y, capital Y, power z, which is a half. So in other words, this is the same as f is equal to constant k times y power a half divided by density power a half, and then divided by the L. And this, when you summarize this, it will give you our equation as required. So I'll end up with my f being equal to k out of L, the square root of y out of the density rho, as my final equation, which is the same as the one given up there. So that is wonderful. Which part did you pass? All right. So below this video here, we'll have some more questions that you can try out. Let me put them there, and you get yourself. Then afterwards, we'll be doing the quiz in the next part. Otherwise, thanks for being part of this lesson. See you.